In this video, now that we've finished talking about atoms and molecules, we're going to start talking about chemical formulas and composition of molecules. There are three different ways to describe a chemical compound, or three different formulas. The first two are empirical and molecular formulas. An empirical formula identifies elements present in terms of the simplest whole number ratios. That is, when you deal with table salt, for every one sodium atom, there's one chlorine atom. In water, for every one oxygen, there are two hydrogens. And so those are empirical formulas identifying all the elements in the simplest whole number ratio. The molecular formula, on the other hand, identifies the actual number of atoms in a molecular compound. For instance, if you look at a molecule of water, then for every one oxygen atom, there are two hydrogen atoms. That is one molecule of water. Now, this is different from, say, salt, table salt, sodium chloride, because the way that table salt looks is you have a whole bunch of sodium atoms that are connected by a chlorine atom. It just becomes a grid of sorts, a lattice. And so it is impossible to identify one sodium atom with one chlorine atom. And so really it's not an individual molecule, it's a chain of atoms forming a series which we know as table salt. So how can we tell whether it's formula is empirical or molecular? Well, an empirical formula is generally ionic, meaning it lacks discrete units or discrete molecules, as we saw with the example of table salt. And an empirical formula or ionic compound is generally composed of both metallic and non-metallic elements. That is, one element from each side of the periodic table, the metals being on the left-hand side, the non-metals being on the right-hand side. If you were to take an empirical compound and calculate the electronegativity difference between the two atoms of the compound, you would find that that difference would be greater than 1.7. If that's the case, you know you're dealing with an empirical formula. On the other hand, a molecular compound is generally created using covalent compounds, covalent bonds, generally found between two different nonmetals, a nonmetal bound to another nonmetal. Now, molecular and empirical formulas can be different. Here's a great example. Let's take a look at glucose, that is sugar, the type of sugar that we cook with. One molecule of sugar, of glucose, is found as C6H12O6. That is, one molecule has 6 carbons, 12 hydrogens, 6 oxygens, all bound together. But the empirical formula, remember, is the simplest ratio, which means that for every one carbon, there are 2 hydrogens and 1 oxygen. And so that's the simplest ratio. And so you can see the difference between the molecular formula, which talks about one entire molecule, and the empirical formula, which just talks about ratios. Here's the third type of chemical formula. It's called what we call a structural formula. This is more of a graphical representation of the arrangement of atoms within a molecule. For example, let's take water. The molecular formula, as we just learned about, talks about the exact number of atoms in one molecule, H2O. Well, what would it look like? That would be here in our sketch. That's what the atom would actually look like. And so we try to represent that as best we can using the structural formula on the right-hand side. using single lines as single bonds, or in the case of carbon dioxide here at the bottom, CO2, we use double lines to indicate double bonds. So this is a great way to represent the 3D structure of a molecule in very, very simple notation. This is used heavily in more advanced chemistry, and when you get into things like organic chemistry, it's used all the time. Now let's talk about formula weight and molecular weight. Formula weight is the sum of all atomic weights of all of the atoms in a single chemical formula. In contrast, a molecular weight would be the formula weight of just one simple molecule. So formula weight would be talking about a whole series of atoms and molecules combined together. Molecular weight is looking at just one single molecule. Now, sometimes we do use the term molecular weight to describe non-molecular substances as well, though technically it's kind of a misnomer because molecular indicates one molecule. It still is used for non-molecular substances as well. So here's a great example. Let's take sucrose, another type of table sugar. Sucrose is C12H22O11. In other words, 12 carbon atoms, 22 hydrogen atoms, 11 oxygen atoms in one single molecule. We want to know what is the molecular weight. The first thing we need to do is take the atomic mass of carbon, which is 12 atomic mass units. But there are 12 carbon atoms, so it's 12 times 12. We also need to add the 22 hydrogen atoms. Now, hydrogen has an atomic mass of 1, since it's merely one proton in the nucleus, but there are 22 of them. We also need oxygen, which has an atomic mass of 16, but there are 11 of them. So if you take 12 times 12, 22 times 1, and 11 times 16, then you get a total of 342 atomic mass units. That would be the molecular weight of sucrose, table sugar. Now, when we talk about the percent composition of compounds, we're not talking about actual weights or masses. We're talking about how much of a substance is made of, say, carbon or something. How much of your sugar is made of carbon. Talking about it as a percentage. So the way we calculate the mass percentage of an individual element is we take the atomic weight of that element. So, for instance, if we want to know the percent of carbon in the one we just found, C12H22O11, then we take the atomic weight of the element, which would be carbon. It has a mass of 12 atomic mass units, 12 of those. Oh, excuse me, that comes in right here. The number of those atoms, there are 12 carbon atoms. And divide that by the entire formula weight, which we just found as 342 atomic mass units in the previous slide. Then we multiply that by 100%, and you get the total percent of the element. So for instance, here, this example we've been doing, carbon has a mass of 12 atomic mass units. There are 12 atoms. That gives us a total of 144 atomic mass units divided by 342 atomic mass units, which is the total formula weight. Multiply that by 100%, and we get 144 divided by 342 times 100% gives you 42.1%. So 42.1% of C12H22O11 is made of carbon. And that's what we're talking about with the percent composition. So let's do another example. This time I'll break it down into individual steps so that you can see, and then we'll get a really important point at the end of this. Let's talk about sodium fluoride. We often add this to water supplies and also to many toothpastes so that we can add some fluoridation for the health of our teeth. So we want to know what percent of composition of the elements of both sodium and fluoride is in this compound. So the first thing we do is we write the formula for sodium fluoride. Voila. Sodium Na and fluorine F. Sodium fluoride is NaF, excuse me. Okay, the second thing to do is we determine the formula weight. Well, formula weight of sodium is the atomic weight of sodium is 23 units. There's only one sodium, therefore the total is 23 units. Fluorine has an atomic weight of 19 atomic mass units, only one fluorine atom, so its total weight is 19. Therefore, the formula weight is 23 plus 19, or 42. Now we need to determine the percentage of both sodium and fluorine in our compound. So sodium, we take the atomic mass, 23, multiply by the number of atoms, 1, divide by the total formula weight, 42. If we calculate that, we get 54.7%. 54.7% of the atomic formula weight is sodium. If we do the same thing for fluorine, fluorine has an atomic mass of 19 atomic mass units. There's only one atom, so 19 times 1, divide that by the formula weight, 42, gives us 45.2% of the molecular weight is fluorine. Now, I want you to notice something. If you add 54.7% for sodium and 45.2% for fluorine, notice that only adds up to 99.9%. What happened to the other 0.1%? Well, often the total doesn't add up exactly to 100%, and this has to do with rounding issues. The atomic mass of sodium isn't exactly 23. It would actually be 22.98976, so on. And likewise for fluorine, the atomic mass is 18.9984, so on. Not exactly 19. So because there's rounding in those numbers, then we have a little bit of a rounding error, so it only totals up to 99.9%. All the same, this is a very simple and easy way to get close numbers to determine the percent composition of specific elements in a compound.